Quantum computing sounds like something pulled straight out of science fiction, but it's very real and it's developing fast. To understand what makes it so powerful, we first need to understand how it differs from the computers we use every day. Traditional computers, the ones in your phone, laptop, or gaming console, process information using bits. A bit is simple. It can be a 0 or a 1. Everything your computer does, from loading a video to running a game, is built on long strings of these zeros and ones. Quantum computers use something fundamentally different called qubits, short for quantum bits. Unlike regular bits, qubits are not limited to just 0 or 1. Thanks to the rules of quantum physics, a qubit can exist in a state called superposition, where it can be 0, 1, or both at the same time. That single difference changes everything. When multiple qubits are combined, their ability to exist in multiple states simultaneously allows a quantum computer to process a massive number of possibilities all at once. Instead of checking one path at a time like a classical computer, a quantum computer can explore many paths in parallel. Another key concept is entanglement. When qubits become entangled, the state of one qubit is directly related to the state of another, no matter how far apart they are. Change in one instantly affects the other. This connection allows quantum computers to coordinate complex calculations in ways that classical systems simply cannot replicate. So what does this actually mean in practice? For certain types of problems, quantum computers have the potential to be dramatically faster than classical computers. One well-known example is factoring large numbers. This might sound like a simple math problem, but it's actually the foundation of modern encryption systems. Many security protocols rely on the fact that while it's easy to multiply large numbers together, it's extremely difficult for classical computers to reverse that process. A significantly powerful quantum computer could break these encryption methods by solving factoring problems far more efficiently. This has major implications for cybersecurity, banking, and data protection. Another area where quantum computing shows promise is optimization. These are problems where you need to find the best solution among many possibilities, like determining the most efficient delivery routes, managing traffic flow, or optimizing supply chains. As the number of variables increases, these problems quickly become too complex for classical computers to handle efficiently. Quantum systems could evaluate many configurations simultaneously and identify optimal solutions much faster. Quantum computing also has the potential to revolutionize chemistry and materials science. Molecules and atoms behave according to quantum mechanics, which makes them incredibly difficult to simulate accurately with classical computers. Quantum computers, however, naturally operate using the same principles, making them much better suited for modeling these systems. This could lead to breakthroughs in drug discovery, allowing researchers to simulate how molecules interact at a level of detail that was previously impossible. It could also lead to the creation of new materials with unique properties, such as better batteries, more efficient solar panels, or stronger and lighter construction materials. Despite all this potential, quantum computing is still in its early stages. Building a practical quantum computer is extremely challenging. Qubits are incredibly sensitive to their environment. Even the slightest disturbance, like heat, electromagnetic radiation, or vibration, can cause them to lose their quantum state. This is known as decoherence. To keep qubits stable, many quantum computers need to operate at temperatures close to absolute zero, colder than outer space. Specialized equipment is required to maintain these conditions, making quantum systems complex and expensive. Another challenge is error rates. Classical computers are very reliable. Errors are rare and can be easily corrected. Quantum computers, on the other hand, are much more prone to errors due to the fragile nature of qubits. Researchers are actively developing quantum error correction techniques, but this requires adding many more qubits just to stabilize a smaller number of logical qubits used for computation. This means that even though some quantum computers exist today, they are still limited in what they can do. These current systems are often referred to as noisy intermediate scale quantum devices, or NISQ devices. They are powerful enough for research and experimentation, but not yet capable of solving large-scale, real-world problems that outperform classical computers across the board. That said, progress is happening quickly. Major technology companies, research institutions, and governments around the world are investing heavily in quantum computing. New hardware designs are being developed, including superconducting qubits, trapped ions, and even topological qubits, each with its own advantages and challenges. At the same time, researchers are developing quantum algorithms, which are the instructions that tell a quantum computer how to solve a problem. These algorithms are very different from classical ones, and designing them requires a deep understanding of both computer science and quantum physics. One important thing to understand is that quantum computers are not meant to replace classical computers. Instead, they will likely work alongside them, handling specific tasks where they have a clear advantage. For everyday activities like browsing the web, watching videos, or writing documents, classical computers will remain the best tool for the job. Quantum computers are more like specialized problem solvers. When used in the right context, they could unlock solutions that are currently out of reach. There's also a growing focus on quantum safe cryptography. Since quantum computers could potentially break current encryption methods, researchers are working on new algorithms that are resistant to quantum attacks. These post-quantum cryptographic systems are designed to keep data secure even in a future where large-scale quantum computers are available. So when will quantum computers become widely usable? That's a difficult question. Some experts believe it could take a decade or more before quantum computers reach their full potential. Others think certain breakthroughs could happen sooner. The timeline is uncertain because it depends on overcoming significant engineering and scientific challenges. What is clear is that quantum computing represents a fundamental shift in how we process information. It's not just a faster version of today's computers, it's an entirely new way of thinking about computation. As research continues and technology improves, quantum computing could reshape industries, transform scientific discovery, and change the way we approach some of the most complex problems in the world. Right now, we are at the beginning of that journey. Understanding the basics of quantum computing today puts you ahead of the curve, because this is a field that is only growing, this is a field that is only going to grow in importance. And while the technology itself is incredibly complex, the core idea is surprisingly simple. Instead of being limited to one possibility at a time, quantum computing opens the door to exploring many possibilities all at once. That single shift has the potential to change everything. Thank you for listening. You're awesome.